All right, I'm going to go ahead and continue on. I think that the first part of the lecture was salvaged, even though my software locked up there. All right, let's move on to right here. Right there, okay. Again, this gets into a little bit of the same thing. More data buses available, and I hate terminology, but the more, the wider the data bus, I shouldn't say the more data buses, the wider the data bus, I don't like the term better. The reason I don't like the term better is because it just simply means that you can move more data in and out. That's more expensive. Will normally mean a more expensive CPU and computer. That is true. If you're talking desktop computers, then that's generally true. You know, you can't buy an 8-bit desktop computer anymore. They had quit making those in like 1986, I think, the last 8-bit. Like the original Apple IIs that were sold, those were an 8-bit microprocessor. They used the old 6502 microprocessor. Actually that was a very popular microprocessor. So did the L2 or the Ataris use that. The Commodores used those. So a lot of the early home computers used 8-bit microprocessors. The original big computer that a lot of the computer geeks used was the old Altar that used the 8080. That was or one of the old early computers used the Z80. There was a lot of 8-bit microprocessors out in the early 80s that they quit using that there. The original IBM PC, and again we're talking about 1982 that this came out, used an 8-bit, 16-bit. So it had an 8-bit bus externally, but inside the chip it was 16-bit. So it was a very confusing microprocessor to teach because it's a 16-bit microprocessor when you deal with the internal software, but when you deal with the external hardware, it was a 16-bit microprocessor, or 8-bit microprocessor. It was a very confusing one. Since then, the 186 came out, and 286, 386, 486, the Pentiums, the Core 2s, now we're at the i5, i3, i5, and i7 categories. These are all the Intels. They're all getting up to 64-bit processors. So that data buses are bidirectional. The processing power of the computer relative to the size of the bus. That's again relevant. I'm sure I mentioned that there. The term better. The reason I don't like the term better is because it implies that if you have less than 64 bits, it's a substandard computer. It depends on what you're using it for. If you're designing a computer system to control a refrigerator, and your refrigerator does 4 or 5 functions. You open the door, it turns on the light's on too long, it sounds an alarm. It keeps the temperature at a preset level. It might show the temperature on a little display in the front. That there. If you have an ice maker, it monitors how long the ice has been in there and tells the ice maker to fill up again. But it does a series of fairly basic functions, right? Putting an i7 processor in a refrigerator doesn't make any sense. That's like you're trying to hammer nails and you bring in a 15-pound sledgehammer. It's definitely overkill. So when you talk about better, it's what's applicable to the application. And when we deal with microprocessors, there are situations where a microcontroller won't work. We got to go with a microprocessor. You try to find the smallest and cheapest device that does the job. That's part of engineering. You have to figure out how much do you need to get this job done. So when you're designing a system around microprocessors, you look and you try to estimate. Will an 8050, this particular 8051, like the one at Pepsi, I need more I/O. All right, can I get that by going to a little bit bigger one back there? Do I need analog? All right, I need to pick a device that's got analog I/O. I need to be processing images and I need to be downloading files. I need to be doing that. Well, I can't use a microcontroller. I'm going to have to go to a full-blown microprocessor back there. So you tend to have to look at the application. So
this slide is coming from someone who's talking from the idea of a computer system, a desktop computer, not an embedded application. And I will be real blunt and say 90, in this room, I would say probably half or more of you will run across times in your career you'll be looking at embedded applications like probably none of you will be designing motherboards for desktop computers. That's a very niche market. You know, there's only 3 or 4 companies out there that do that. Asus, Gigabyte, Intel. I mean, there's like 5, you know, probably a dozen companies that do that. And most of those companies are either in Taiwan, US, a couple in Europe, and the designs are pretty much off the shelf because those designs are dictated by who designs the chipsets on the motherboard. And that's actually designing the actual digital I/O that talks to that there. So that's a very niche market, designing computer motherboards in. That's why I'm moving this course a little bit away from motherboard design and microprocessors and in toward more of the embedded systems type application, because that's really what you're going to see. So and that's why those who took this course before, they had the 8086. You can see why my skin crawled when I saw that they used the 8086, because that's not what you're going to see. You're going to see PICs, you're going to see micro 8051s, you're going to see various ones like that. Okay, address bus, the larger the larger the devices that can address there. Now, memory chips are multiple sizes. We'll talk about that there. You can have a 8 gig module. They make now, I haven't seen 32 gig modules, but I've seen some 16 gigabyte modules right there. Now that's usually 9 chips on one module right there. And depending on the motherboard, you might put them in pairs or you may put them in single that there. But the more lines in the address bus, the more addresses you can locate out there. It doesn't necessarily mean larger devices. It could be a lot of smaller devices. It could be several very large devices. I know that my particular, not this laptop, but even this one here has got 8 gig of RAM in it. I think we determined these have 2 gig RAM in it or 4 gig of RAM out there. So some motherboards you buy will address only 8 gig of memory, even though the processor will address far more. That has to do with the design of the motherboard on the computer. We're not going to be designing motherboards, so quite often we're going to get down to a much narrower application. So, okay, the address bus is unidirectional. I mentioned that before. This is kind of the same example. There is an exception to that rule, and I'm not going to dwell too much on it, but there are some systems that have what they call a memory manager that does what they call a direct memory access, a DMA chip that you put in your system which allows it to move a large block of memory to another large block of memory without going through the microprocessor. It's uncommon anymore. I've used DMA chips when I was moving, for example, an image from, say, a satellite picture into the microprocessor before we started processing it, because it was too slow to use the processor back then. Nowadays, the processors are much faster out there. So DMA, access is not all, but you might hear that term DMA. That's direct memory access, where you bypass the microprocessor. And when you do that, you have to have a processor. You can tell it to stop. Out there, stop. Wait 3 seconds while I manipulate your memory. Out there. So it's uncommon, but there are exceptions to that rule, is all I'm pointing out there. Okay, for memory to process information, it must be stored in RAM or ROM. That there provides, initially, that's not permanent changes, various, out there, that's kind of repeat there. There is what they call secondary memory that transfers memory to the RAM. That's probably, some of the early disk controllers also use DMA. I should point that out. That, some of the early hard drives, in order to speed things up, it would stop the processor. It would grab the memory from the hard drive and write directly to the RAM. That was another application where DMA was
was common that there. So, all right, now we're getting into the internal registers of the microprocessor right here. What we're talking about here, and these slides are going to be looking at the 8051. Every microprocessor has registers like we're talking about. But they're all different. This is where things vary. I'm going to pick one, and I'm going to probably venture back here in a minute and pull the 8086 book up and show how it's different. That's there. So, that there. It uses registers. Anytime you're working with a register, things are much faster because you're on the piece of silicon. In the digital world, it was all one piece of silicon, and that's the IC. That's the thing that's got the legs on it. That there. That's a piece of silicon. You can do things much, much faster than if you have to leave the silicon, go onto the board, and go to another piece of silicon. Anytime you talk to other memory devices, you've got resistance in the wires, you've got resistance in there, you've got straight capacitance, you have to slow down, right there. Just like when you get on and off a highway, expressway. You have to slow down. So if you're getting off one highway to another highway, you have to go on the exit ramp, you slow down, you go on the exit ramp, when you get to the next highway, you can speed back up again. So anytime we got to go off the processor to the outside world, and then when I say the outside world, I'm talking about other chips on the board, not necessarily to the real world, we have to slow down, right there. So in order to do things internal to the processor, it makes things faster. Now, in this class, we're going to be doing a lot of manipulating with registers. Quite honestly, as a system designer, I probably have not manipulated registers by hand in probably 10, 15 years. I let the software that compiles my code handle that. But since we're goal of this class is to learn how microprocessors work, we have to see the internal workings of that. Will you ever use that in real life? No. So I'm telling you up front that some of what we're going to be looking at is not worthless in the sense of worthless because it's background information. But when you start doing this, you have to know what's happening and why, right there. So when we look at the register, that there is that the more registers you add, the more expensive it is. The bigger the piece of silicon. Now the rules change a little bit when we talk about microcontrollers. And the reason the rules change there is now we're putting the RAM and the ROM on the same piece of silicon. There. So that's one of the advantages of microcontrollers. The disadvantages is because we typically have a much less powerful processor in order to fit all that in there. So, all right, let me just keep on going here. Right here. This is kind of a series of this here, and as I determined before, I'm good for about an hour and a half. We're not going to run all. We don't run all the way to 2 o'clock. Actually, we're supposed to run all the way to 2:15. There, started. Well, that's why I'm feeling like I'm going fast. I'm thinking that my mind's thinking we start at 12. I'm already left cut you guys loose at 1:15. I'm sorry, I'm not used to these 15-minute starting blocks. Okay, we've got a number of these registers here. Some of these are very much the same across that there. In almost every case, we've got what's called the ALU. This is the arithmetic logic unit right there. This is the heart of our microprocessor. This is our finite state machine that tells everything. Right there. So that's there. We've got, these are all internal buses. Now going to the outside world, we've got to the data bus. We've got our instruction decoder, timing, and control. This goes to our control bus. Our instruction register actually holds our current instruction. Our program counter, and we'll be doing a lot with that program counter from time to time. It's that keeps track of where we're at in our code, right there. And then we've got a series of internal registers, and these all vary between processes. Over here, we have a series of what's called flags. flags are exactly that. The processor raises a flag when something happens. We subtract two numbers, the result is negative. We've got a flag. We add two numbers, we had an overflow. That sets a flag. That there. So we've got various flags that we set there. We do a comparison between two numbers, and if they're equal, it sets a flag. So if we can look at those flags, and we can do things with them. There's commands that call jump not zero. What jump not zero does is it looks at the zero flag. If it starts set, it jumps to another address in our code. Right there. It looks at those flags. Right there. We have jump negative. Right there. So we can look at these flags, and they help us with what's happening. If we add two numbers and there's an overflow, we know we need to compensate for it. Right there. So we have those flags are very, very useful. Otherwise, things like comparers don't work. Now, how many programming have you had? Most of you go up to, of course, the C, right? C program. So if you remember, in C, there's a command called if, right? Right there. So, so if you do an if, you're comparing two things. If A is equal to B, then do this, or else do that there. The C doesn't have jump commands. They have calls where you call functions. We have those, but C doesn't have jump commands. So what we have to do is we have to work around them. We also don't have if that else. We have to generate code for if that else. So we're working on much level. That there. But then we have the internal workings of that there. If I want to add two numbers together, typically I bring one number into A, one number into B, and then I add the results together and store it in A. Right there. I don't add. So before I typically can do anything with numbers, anything in terms of math, I have to bring it into the processor, and I stick it in these internal registers in order to manipulate that there. So this is what's inside of our processor, right there. Right there. So this is kind of an explanation of what's going on there. ALU performs, arithmetic logic unit, right there. It performs math. Program counter points to the next instruction to be executed. So if you do a jump command, what that does is take what is ever in the program counter or there and replaces it with the address that you have in the jump command. Right there. So really what a jump command does is it changes the program counter for you. Right there. The instruction decoder takes that there and looks at the instruction and decides what it needs to do. Capable of instruction requires more transistors design. I'm going to take a little bit of a sidestep here and talk about there's two types of processors. We already talked about two types already. Now there's another two types. The two types we're going to be talking about in more detail in this class are the general purpose microprocessors and the microcontrollers. I mentioned before, general purpose microprocessor, and I mentioned the microcontroller. A microcontroller is a processor that has internal to it the memory and the I/O and sometimes analog and things like that. There, that's the microcontroller. There, the microprocessor, all that stuff outside the chip, and you have to have additional chips. Obviously, a microcontroller system is much smaller because you've eliminated the RAM chips, you've eliminated the ROM chips, you've eliminated the I/O controllers, you've probably eliminated A to Ds, D to As. Most cases you eliminate the clock module and all that stuff. It's all right inside the same chip. Right there. The disadvantages is microcontrollers tend to be relatively small. I don't know, the board that I passed around, that's only a 20-pin IC. I mean, that's a very small processor, and yet that will probably run any household device you have other than your cell phone or your computer or your TV or things like that. And obviously, televisions have a lot of high-end processors for processing images. Image processing takes a lot of processing. A lot of processing. So, the next set of division, and there's what they call RISC and CI and CS.
And those are, let me write those down right here. Right there. We have what's called a RISC processor. Right there. Right there. And a RISC processor, RISC, is a reduced instruction set computer. I believe it's computer, computer. And the other is CICS, which is the same, only it's complex or complete, depending on who writes that. Most people use complex right there. There's advantages and disadvantages between both of these. The 8086 is a complex instruction set computer chip there, and they probably should put P at the end instead of C for processor right there. Where the RISC is something like, for example, a PIC microcontroller. It only has maybe a dozen, 24 instructions in the instruction set. An 8086 has got several hundred instructions in the instruction set. The RISC compilers or the RISC processors tend to operate instructions much quicker. They tend to operate at higher clock speeds and they're much faster, but you can't do as much with each instruction. Because the instructions tend to be, because there's only a few of them, they have to make them very general, very specific. So what you can do with a single instruction in a CICS processor might take 3 or 4 instructions with a RISC. Right there. Because I've got several hundred instructions in this right here. And those instructions might include things like multiply and store data. Right there. Or here, all I can do is multiply. Then I have to do store the data as a separate instruction. Right there. So it may take 2 or 3 instructions. Which one is better? Again, it goes back to the application. Things such as very specific processors tend to be RISC. Does anybody own a Canon digital camera? Everyone knows what I mean about a Canon EOS digital camera, right? I think Nikon's more popular. Regardless, Canon has a chip called the D-chip. And it's a special microprocessor that they've designed, and they fine-tuned it for every generation of cameras. They make it a little faster. And this is a RISC processor, is what it is. It's the processor that controls the camera. It's the one that goes out, gets the data from the sensor, stores it onto the drive or onto the memory card, allows you to process it. It does the image tweaking, adjusts for the how much light you've got. It also stores the movies. And this is a very, very specific microprocessor designed just to process images for these cameras. Is it a general purpose microprocessor in the sense that you can do other things with it? Sure, but it won't work very well for other things. It's designed specifically for camera operation. That's going to be a RISC processor. And it's going to be a very fast RISC processor. And its instructions are going to be unique to that needed for image processing. An 8086 microprocessor is supposed to do everything from bake bread to process words. It does everything. So it has a complex set of instructions that will do almost everything. And you can almost look at these instruction sets as vocabulary that the processor can understand. You deal with a very limited vocabulary, he doesn't have to think very hard to know what these words mean. The more complex it gets, this also creates problems for compilers. This is off the subject, but we really have, at some point in the next week, I probably need to be putting together a whole study guide here for what I'm covering right there. But I've done some work with what for the family of microprocessors called the PIC, which is made by Microprocessor. And some of you might have heard of them, some of you might not. But these are very low-end, cheap microprocessors.
run into up there. So we've got all kinds of, and we really haven't looked at that there. So this is kind of an example here. We've got a CPU that's got 4 registers, 8-bit data bus, 16-bit address bus, flash memory from 0 to FFFF, that they're moved to register there. So what we're looking at is the start of how this thing, how we program this thing. So what we've got here is, this is the code, is move a value to register is B0, and the code for adding a value to that register is A4. So we have to put the data in there in order to add, and we have come up with a fairly basic program. And I probably will end after this discussion, because this is probably a good place to stop right there. So this gets back to right here. This is the instruction right here, right there. And this is the way that it looks in memory. So this is our memory address, and this is our program there, right there. So we're going to place into that there, move into code for moving a value in the register A right there. So we're going to, it's going to be stored there as B0. That happens to be the code. The actual command for that might be something like let's move A, comma, number 21H. In other words, that might be the actual code that we would write for that. That there. So what that does is it moves the number 21 into register A, right there. Well, what the microprocessor sees is B0. That happens to be the magical code for move the following data, you know, whatever is stored in the next location, into register A. Then the next one is take the what's right there, whatever, you know, code for adding the value to register A and the value to be added right there. So 04 is going to take whatever we moved into A. So A contains 21 right there. Then we hit it with a 0442. Well, 0442 is going to simply now add that to 43 right there. It's going to change that right there. Then we hit it with another 012. So that's so after. If we look at A at this point, A contains 21 hex. Right there. And what did I do there? I hit the right there. So at this point right here, A contains 21 hex. Right there. At this point here, it now contains 63 hex. At this point here, it now contains 75 hex, because we've added 3 numbers together right there. So our code would probably look something like this there, and I'm going to just jump out of here and right here. Our code for this is probably going to be hopefully this. Oh, this. Why is my OneNote not cooperating here? I have OneNote up here. That wasn't very. Well, now my battery's about up there. Okay. OneNote. Send a OneNote tool. Okay. Okay.
our code is probably going to look something like this. Move into A 21 hex, right there. Add to A 42 hex, add to A, what was it, 12 hex was the last one? Right there in the example. All right, I'm just going to say 12. 12 hex and halt right there. Now, this is not necessarily the language that we're going to be using, but it's going to look something like this. Most somewhere look this way. So, and what they said is the opcode for move to A was B0, right? And the opcode for add was, that's the opcode for move, and then the opcode for add was 04, right? So the job of the assembler is to convert this into something that looks like this. B0, 21, 04, 42, 04, 12, and I'm just going to say, I can't remember what it is. It doesn't matter because we're doing an arbitrary process, so we're just going to say FF is halt right there. So what the assembler does is take our instructions that are as clear as mud to everybody, right? And converts it into something that's completely cryptic right there. But the job of the assembler is to generate this code. And these are the instructions that are stored in memory that the processor needs to know as we go through and execute our code. Now, obviously, if we're writing code like this, to generate the code to do a whole lot is very difficult. Our programs in this class, at best, are going to be adding a couple dozen numbers and doing some basic things right there. You know, we're not going to be writing code to solve quadratic equations even. Out there. The code to do that is very complex in assembly language. Out there. And keep in mind that the output of a compiler, such as the C compiler, takes your C code and converts it into something that looks like this. And then it runs through another pass that converts it to that there. So back in the early days, when I first started working with microprocessors, we all carried around little cards in our pocket for the SK, for the 8085, that we would write our code on a pad like this. And then we would go through the card and we would look up the opcodes and we would write this on the side. We would do that by hand. And then the assemblers came out and that skipped that one step right there. We didn't have to do that. And then finally compilers came out that were usable, that we could skip this whole thing altogether. But once in a while, you're forced to come back to this level. You know, you've got a piece of code that doesn't work. That's there. You got to look at, sometimes you have to look at the assembly code. I've actually used compilers for microcontrollers that the compiler itself had errors in, and I had to go back and correct the assembly language code. Because the compiler was in, my code was right in C. The C code was simulated right. The C code was perfect, nothing wrong. But the code generated by the C compiler was wrong. The compiler itself was generating that code. And that's part of the challenges you have when you deal with microprocessors. Because you rely on tools that are designed by other engineers that hopefully they're more confident than, you know, than you are at the time, but maybe they're not. But people do, but compilers do generate errors. And when we're dealing with the
not as many users. Right there. So when we move to the embedded world, it's more likely that we're going to find problems with our tools because there isn't as many users. And the tools are specific for a particular type of code. And you gotta remember that every microprocessor or every microcontroller family has a different compiler. Right there. So if you're using a PIC 16F microprocessor, the microcontroller, it has a different compiler than a PIC 18F microprocessor because the opcode is slightly different. The 8051 is going to have a different compiler than a PIC. So every family, an 8051 is going to have a different compiler than an 8086. Every processor has a different compiler. Now some of them are common and just have differences in the registers and things like that, but for the most part, it's a unique tool for just that application. Got it there. So you tend to run into that there. I'm going to stop right at 145 right there. Is that what you got there? So I talked to some of the other instructors. I guess they just BS for the last half hour. Is that what they? It's going to be posted. That there. But I'm just going to go ahead and stop at this point. Is there any questions? Any comments on where we're going? That there. Now, some of you are shaking your head as if you understand now. I may have to come up with a pop quiz to see where you understand. Right there. Oh, that there. I need to see whether you're really listening. You act like you understand my English, but are you really? That there. So, there. But really, we're going to be getting to the point that we're going to be looking at more specifically. This has been still pretty much introductory material. Now, this today should be fairly new for those of you that have just seen the visual world. You haven't seen a lot of this. You did see this visual, right? So we are moving to the newer material. All right. I guess I see everybody again tomorrow. Is that right? Yes. Yeah. I haven't figured out what we're going to do tomorrow. There. It may be. We got 2 hours, but what I may actually do is it's supposed to be full lab time, right? What I'll probably do is between now and tomorrow, I will bring up I'll get the software installed on here, at least kind of go through a demo on how the tile processor, assembly processor goes, and I've downloaded the board and simulating the board. I'll just kind of go through a demo on that. It won't take more than probably 45 minutes. So that's really, you guys what, in this room here, what, 8 o'clock is it, or 10 o'clock? What's that? 8 o'clock in this room? So, all right, it'll be, like I said, what it's going to be is just basically some demonstrations of how the tools work, how everything's plugged in. We're not ready to do real labs yet, but kind of go through this type of assignment, how it's actually done, how you would actually do that in a lab situation out there. And I probably would